Okay, just some comments without going to the board. In section 12.6, I believe, number 33, centroid of a solid and so forth is fine. But I wouldn't keep writing out a density delta. If you're doing the centroid, you can always assume that the density is 1 because you know at the end that when you divide the moment by the mass, you're going to have a delta both in your numerator and denominator, so it never had to be there in the first place. Made a little note that the center of mass of the sphere in the first octant, or the centroid, is the sphere in the first octant. The result at first seemed to me a little bit low. It's only about 1/8 of the radius of the sphere from the origin in each direction. I'm still a little uncomfortable with that, but so I'd maybe think about checking that out. Just my intuition could be off there. I didn't say anything wrong in the steps, but it's easy for me to miss something like a factor of 2 or whatever. Another one, finding the average value of the function x, y, z over a solid sphere centered at the origin, no matter what the sphere, that's going to have to give you 0 by symmetries. X, y, and z can each have either a positive or a negative sign. So by that, there are 8 possible combinations of signs, and that kind of naturally breaks things into octants. And if you pair up the octants where the signs of the x, y, z are opposite, then you can arrive at the same result by symmetry, even though what you did was absolutely what we wanted you to do. Just kind of think about the symmetry of the situation. It wasn't that much work to do it by doing the integrals. And again, that's what we wanted to see done. But you can also reflect a little bit on how symmetry arguments can save work. Radius gyration looks good. There's a problem here with the work to raise water in a cylinder a certain distance. I made a couple of notes. I'll probably do that on the board just to make sure we have that right. But for example, at the end I see quantity h minus z equals h, which would imply that z is 0. And in the result that you got, there's assumption that the center of mass is at the origin, but even though the approach looks really pretty good, there doesn't seem to be any dependence of the final result on the location of that center of mass. I could be looking at it wrong. I'll work it out on the board, and we'll see how that one comes out. Yeah, here's one on the moment of inertia, number 53. It's probably in, I guess it's still in 2.6. Rectangular homogeneous lamina, H by L. You got a moment of inertia about the y-axis. And it's an axis through the center of mass. I'm going to have to take a closer look at that one because there are a lot of different axes through the center of mass. And it appears that we assumed one where the lamina was oriented parallel to the x and y axis, and we used the y axis through the center of mass. Do it diagonally, you do it horizontally. Do it in any direction. So do we always get the same result? Is there a unique answer to the question? So we'll probably take a look at that one on the board a little bit. Good application of the theorem of Pappus. In 12.7, let's see what we have. Yeah, I have a note on number 38, but then I took a better look at. Actually, the thing confused me is use I. So, thinking, what are you doing? You're finding the center of mass and moment of inertia of this thing. Looks like maybe you're using I for the integral, because what you have there is just, you know, what you get from the integral. So, you've never seen me do anything like that. If I stands for integral, capital I stands for integral, then it looks okay. If it stands for moment of inertia, about one axis or another, then there might be a problem there. The one about using spherical coordinates to find the, the one about the cone within a uniform cylinder through the origin between z equals square root of x squared plus y squared and half of square root of x squared plus y squared. So you got two different slopes here, and you rotate that around and you cut a cone out of the sphere. And it was done in, I believe, polar coordinates. That's another good one that would be useful to look at in rectangular, spherical, and cylindrical coordinates. And I'm probably going to come back and work through that one in spherical coordinates because it seems that's the more natural. Since cones with apex at the origin are very naturally described in spherical coordinates in terms of the angle phi with the z-axis, and spheres even more easily. Seems that would have been a simpler integral. There's a question there, but it's okay. See what else we've got. I think that might be it, but let's just see if we get these pages to separate. Yeah, so, you know, everything looks pretty good, just a couple little things, and then a couple little things that I just kind of recommend you give a little more thought to, think a little more deeply about some things like symmetry and uniqueness and so forth. Okay, so looks good. Let's look at that sphere.